Badru Ssenoga, and I'm here to present more ways for attaining optimal model complexity. And to know this, you need to first know what is model complexity, because you need to know that one of the things we need to know as we start this topic is to know what is a bias, what is variance, and then you're able to tell what is high bias, what is high variance. When you know this, you'll be able to easily understand how we can attain optimal module complexity. So bias, in a few words, that it is the algorithm tendency to consistently learn wrong things without taking into account relevant data or relevant information in the data. Yet, so meaning that if you want to track high bias is a result of the algorithm missing the relevant relationship between the features and the target output. So whereas the variance is about the algorithm's sensitivity to small fluctuations in the training set, and then high variance is about the results of the algorithms fit into the random noise in the training data set. So if after understanding this, we get to know now what about module complexity. This is about a measure of how accurately the machine learning model can predict unseen data. That is the data that has not yet been put into the model, as well as how much data the model needs to see in order to make good predictions. So that is the data that is the predicting unseen data, that is to control overfitting, and then how much data the model needs to see in order to make good predictions, that is to control underfitting. So the optimal model complexity is that middle line with dots, and then we have to look at the total error as well, which is the bias plus variance, the sum of bias and variance plus the reducible error. So in brief, there are situations when the model performance is impacted even after supplying good quality data, and this is a common problem. And the common problem is the high bias, which is underfitting, and then high variance, which is overfitting. So we've looked at that already, whereby with high bias, you realize that it's underfitting. Then with high variance, it is overfitting. So we want a model whereby it is just right. We want to find a middle ground, or a right fit, a place whereby it shouldn't be overfitting or underfitting, but just right, whereby you will find that middle ground. So we want something that can be able to be or generalize or put in any different model, and it should be fitting. Shouldn't work 100% accurate, but as long as it is optimal and it can be able to work with different models. So the relationship between model complexity and training test prediction error, we want to know that if you see this graph, there is the loss at the vertical axis, then there is the horizontal axis, which has model complexity. You realize that as model complexity increases, the training loss, it decreases, and then as the model complexity increases, the generalization loss increases, or the training loss, or the test loss. The generalization loss is the same as the test loss, it increases. So you see that gap there, the gap there shows it's an indication of overfitting. So, but as you see the model complexity, if it is less, realize the training loss is high, and then the generalization loss is also high, and there's the little space which indicates underfitting. So what are some of the other ways? Because we realize that we have already looked at hyperparameter tuning as one of the ways of attaining optimal module complexity, which is about choosing a set of optimal hyperparameters for fitting the algorithm. We've also looked at regularization, which is a technique used in reducing overfitting by discouraging complex module in some way. So what are some of the other ways you can attain optimal module complexity? So to fix high bias, adding more features can help, whereby let's say you're given length and width of a plot. What about you find another feature such as a plot size? I believe you can get the plot size as a new feature because they have given you length and width. So that is one of the ways. Then the other way is to use early stopping to help training when the model has reached the optimal complexity. So this is whereby if you train this model, then when you feel like, or when it reaches until that validation error, when you see it has reached that validation error and it has started increasing, then stop the process of training right away before it goes into overfitting. So you can go ahead and train the model, the model until the validation error, so that it doesn't go again to overfitting. So that's one of those. Then the other way is to use assembling methods to combine the prediction of multiple simple models, resulting in a more complex model that is more accurate than individual models. So here the principle about ensemble methods, the principle is about training multiple learners for the same problem and then combining them for prediction. So one of the assembling methods, the boosting. Boosting is the assembly technique whereby it learns from previous predictors' mistakes and then making better predictions in the future, but it is learning from the previous predictor mistakes that were made, and then it is able to make better predictions. So when you do that, it's one of the ways you can attain optimal module complexity. Then use feature selection method to identify and remove irrelevant or features from the training data, which can reduce the complexity of the module. So those features that we don't need, the dirty data or whatever data that we have that is not going to improve the performance of the model, why don't we remove them? So when we remove them, that is one of the ways we can attain optimal module complexity. Then another option is to experiment with different module architectures, such as shallow versus deep networks, to find the optimal architecture for the given problem. Because for shallow neural network, it consists of one hidden layer, so features can learn independently. Then for the deep neural networks or deep networks, it involves 2 or more hidden layers. So depending on the problem, what are you going to use, which particular module architecture are you going to use? So it is better to experiment with different module architecture then until we get that optimal module complexity. And then use cross validation, whereby you can use, it's a technique whereby we can reduce overfitting by splitting the data into multiple sets and training on each set in turn. This will allow us, it will allow the model to train on different data and prevents it from being overfitted to a particular set of data. So it's another way that we can do, and that is the reference. Thank you very much.